Hello everyone. This is Silver Martin with Asingwe Eric, and our topic for today is about multimodal feature extraction in machine learning. So when you talk about multimodal feature extraction, you can think about this in a way of uh, us giving these models the ability to have senses. So the models that we've been having usually work with a specific data type, let me say text or a video or something. But now we are trying to create a model that is able to have all these just like humans do. So multimodal learning, here we are integrating multiple data types, or we can call them models that uh, process and interpret different data types, right? We can call them modalities. Then here we're trying to understand, we're trying to enhance the pattern understanding of the machine learning model. So we can apply this in very many sectors, such as emotion recognition, autonomous systems, AI assistants, and medical diagnosizations. So with this, we have what we call feature extraction. So feature extraction is what we use to actually transform one data type to another. So this is like a process of transforming the data into a format that the model can understand it. So now here we can see that feature extraction, we are actually transforming the raw data into meaningful representation that the machine learning models can understand. Right? So we have another term, which is dimensionality reduction. So this is like we can use techniques like the PCA, principal component analysis, where we try to scale down to the important details in the data set. Then we also have the techniques. So with this, the techniques, I'm going to talk about them in the next slide. So the types of modalities in machine learning, we have text, have image, have audio, and video. So I'm going to explain more about this. Let me see. Okay, let's start with text. So text, we have something called tokenization. So tokenization is where we get like a sentence or a phrase and break it down into individual words such that we can easily analyze the sentence. So with that, we can use something like FTIDF. So FTIDF is called, FTIDF in full is term frequency inverse document frequency. So this is majorly to identify the keywords in the document or getting the relative words, like words that have close relationship or meaning to each other. Yes, then we have the other techniques such as the BAT and word2vec. So word2vec is like a dictionary for the machines, which captures the semantic relationship between words. So I can give an example of a cat and a kitten. They have a relationship, so their vector coordinates are kind of close to each other than saying like cat and traffic or cat and car, something like that. Yeah, then when we move on to the image, so the image, we use something called the CNN, the convolutional neural networks. So these ones are like filters. You can imagine filtering an image based on like a mathematical equation to detect specific visual patterns. So the more complex you go into the CNN, the more clearer and precise it becomes. So the more the model gets to understand this image and understand the key features that are present there. Yeah, then we also have others such as the HOG, the Swift, and the PCA. Then when we move on to the audio we have something called the MFCC. So the MFCC, this is like just like how we humans tend to analyze audio, we pick up the sound waves, then according to their frequency, we get to understand which words have been said according to how they resonate. So it's the same thing it's the same principle that we apply here. So these ones are designed to capture and analyze the MFCC of the words, and to know which word is spoken. So it's like each word has a frequency to it. Then for other audios such as music and stuff, we use something called spectrograms, which is like a visual representation of the sound waves. So we can check for hidden patterns, and we can do things like determining the journey of the audio or song that has been played. Then for the videos, we can treat videos in different formats. So we can treat a video as a series of pictures or frames. So if we break it down into frames, which is an individual part or individual component in the video, we can apply a CNN to it, such as the one that we used in the images. So with that, yeah, these are the different techniques, and we have gone through all of them and explained in detail. Then we have the strategies, the feature fusion strategies. So strategies, the first one is the early fusion. Okay, so first of all, fusion is a way of trying to combine the different modalities to come up with a single ML model. So it's like we're trying to combine the text and the image to form something that can recognize both text and image at the same time. So how can we fuse this together? So these are the strategies that we can use. So the early fusion, yeah, I can give an example. Let me say a chef who is cooking. So they can either first mix up all the ingredients and then cook them all at once, which is early fusion. Sorry. So early fusion is where we get the all the raw data in the different modalities: text, image, video, and audio. We get those. We get the raw data, then feed them into the ML model. So with that, the model can later learn from that data. Then late fusion is the other way around, where we first process each modality on its own, and then later join up the result that we have gotten. So with this, the early fusion, we can use it to we use it majorly in related data. Let me say, uh, no, the early fusion is usually used in different modalities that have relationship, right? So I can say maybe the facial expressions as one is giving out a message. So there's a correlation between the facial expression and what they are saying. So we can use early fusion. Then for late fusion, if there is no correlation at all, that's when it can come into play. Then with hybrid fusion, we are actually mixing the two. We are mixing the early and the late. So we are mixing the capabilities of the two to come up with a model. Then the attention-based fusion. So this one lets the model focus on different things and learn to assign the weights to them. So I can give an example. Let me say a person watching a movie. They can at a time they can focus on the video itself. Then the other time they focus maybe on the subtitles. Maybe the other time they are looking away, but they are just focusing on the audio that they are receiving. So with the deep learning networks that are currently in the new technology, we can have such a thing applied to the machine learning models. So it can know that maybe I'm analyzing blog posts. Let me assign more weight to the text modality. Or if it's a social media post, an image, that is the modality that is assigned with more weight. So with that, those are the different strategies that can be used to combine the different modalities to come up with a single learning machine model. So with that, let me call upon my group mates to take us through the multimodal machine learning models.
Thank you. My name is Singwil Eric, and I'm going to take you through the remaining part of the multimodal learning. My colleague has talked about different versions. You as a human being, how you process data when you're watching a YouTube video, when you're watching a movie, you're watching subtitles, you're viewing very many things at once and you're analyzing. So we want to try to see how you input such a type of understanding into a person, into a person. Then that's why we come up with a term like multimodal, which is ability to process and comprehend multiple types of data simultaneously. As in, the computer or the machine is able to understand an image, a text, a video at the same time. Then he has also talked about the types of modalities, which are the inputs which we are going to use, or which the machine uses. In this case, we have the text, we have the images, we have the video, and we have the audios. The question you might ask yourself in this case is, how will a computer be able to understand such texts? Because as we know, the computer is unable to understand texts themselves, which are simply the simple things. How will it be able to understand videos and audios? Now, what a computer does, it converts them into vectors. Vectors that a computer can understand. Those are numbers. A computer now weighs, if they are text, the computer weighs the relationship or the difference between two texts, placing them in a mathematical space. Let me say I can give words like king and queen. The computer will comprehend and know that king and queen are closely related. Then there's man and woman. Computer also comprehends that man and woman are similar data and they are related compared to, let me say, another word that could be poet, word, anything else. So those words are put into vectors and measured by the computer to understand the relationship between the words. Then going to the main point, we have what we call, these are the machine learning models. We have what we call the multimodal transformers. Now models like Vilbert, Clip, and LX Smart, these ones, they process texts, images, and they learn them together, form a multimodal representation. I'll give an example of an OpenAI that assesses your text to bring for you images, or an OpenAI that gets both text and image, assesses them, and gives you a result. Excuse me. These multimodal, they learn between two modalities. They gain richer understanding of the world using the images and the text. Then we have what we call, to understand this, you'll have to understand the multimodal alone, then the transformers. Now, transformers, these are neural network architectures that have revolutionized the natural learning process. We have an example there that is called CLIP. Someone might call it contrastive language image pre-training. This is an open AI that associates with images with their corresponding text descriptions. Then going to the next there, we have the autoencoders. Now, as the word autoencoders, these ones, they support unsupervised learning of multimodal representations. As the word unsupervised, this means they learn from data without explicit labels or without targets. And we have keywords like encoder and decoder. Encoder, that means it takes in an input, compresses the data, and then puts it in a lower representation, e.g. a code or latent space, summarizing it. Then the decoder, it takes the compressed representation and tries to reconstruct the output or the original input that the data is accurate, that is accurately possible. Then the next one we have graphical neural networks. Excuse me. These graphical neural networks are specialized type of neural network. They're designed to work with a graph structure, which means data can be having nodes, or which you might call vertices that are connected by edges. Now, things uh, think of things of like molecules.
Harry.
Sorry about that. I think it's a network issue. Uh, so,
You had gone off.
is the video still on?
Continue, continue.
Uh, we have what we call the fusion modes. The fusion modes, they are applied in applications like sentimental analysis. Now, sentimental analysis, we are dealing in cases like emotion, sensitive cases, maybe how the person feels, how they relate to certain environments, how they react to certain videos. Uh, so the the machine is able to understand this. Sentimental analysis can be used in so many cases, like detecting bias, like uh, in facial expressions, body language. Then also have video classification, uh, medical imaging, improving the performance and accuracy of predictions in such scenarios. Next page. Then we have what applications of multimodal data extraction. As you can see, I've talked about the emotion recognition. And the machine is able to recognize using your expression, regardless of what you're saying. Someone has a tendency can say they are fine, yet the facial expressions are showing different things. So the machine is able to the machine is able to realize in such scenarios that this person could be maybe is going through some emotional duress. Then we have healthcare. Now these ones they combine the records with the scans to determine someone's history of medical record history and what they're suffering from, or the history of other people to determine the critical condition of someone's health, what they're going through, able to diagnose a certain uh, drug or diagnose a certain treatment in order to cater for their health. Then we have biometric authentication, that is facial recognition, fingerprint recognition. We have voice recognition. This enhances the security, reliability, and biometric in the biometric authentication system. Sorry. We have the challenges that are faced in the multimodal learning and probably the solutions. We have what we call the data alignment. Now, I'll give an example. Maybe as someone, probably this is a most case, I think someone has faced watching a movie with subtitles, probably, where the movie, either the video is ahead of the subtitles or the subtitles are ahead of the movie. They are not parallel when you're watching a movie where the action, the video, and the audio are corresponding. So that's what we call data alignment. You find a problem whereby sampling models might have not be perfectly synchronized. I use the word synchronized in this case, in the perfect timing. So a solution in this case could be temporal alignment, such as in that case, we have the dynamic time warping, the sequence alignment models, and the cross-modal attention. Another issue could be the sentimental alignment. We already gave an example of a clip before. That is the contrastive learning. Then the next problem we could be having is the dimensionality match. Now, you find the audio, let me see if it's a video again. The audio is not matching with a video, but in this case, you're watching a movie, it could be matching by the time reaches in the movie and there is no audio, which means that these modalities have different sizes. Okay? The audio is less, you've watched the movie halfway, and then the other part of the movie doesn't have the audio. So also modalities have such a problem when you're combining more than two modalities. The solution for that, we could have feature normalization. You
Eric,
scale the features to particular range.
yeah, to add on that, I can give an example of the security system where you use the facial. Now, the modality that uses the facial, you might have like a mask with a mask on, so it cannot recognize the full face with you putting on a mask. So maybe has the eyes and the eyebrows, but the downer part is covered. So that's what I'm trying to say.
Thank you. Then the third problem we have could be missing data. One or more modalities might be missing for some data points. Find they are uneven. One like modality is missing, and that is a significant challenge in this case, as the modality is required to have complete data. The solution in this case, we could have what we call robust loss functions. Now, these ones are designed and they are designing loss functions. They are sensitive to missing data. Maybe you get a warning in case data is missing. Then we also have a dropout. That's also another solution, imputation. Then we can have a fourth problem as computational complexity. High resolution, high resource demand for multimodal processing. Now, here, the multiple modalities can be computationally expensive, especially when you're dealing with high dimensional data or large data sets. It becomes quite expensive to attain some data sets. And it becomes hard for someone or as an engineer or a data analyst to attain some data sets. They become so expensive, you have to pay for them a certain amount of money. You have to apply for them. Some of them, it takes quite a period of time to attain them. Then the solution there, we could have modality selection. If some of them have less information, you consider dropping them to reduce computational cost. Then you could use also the lightweight models. that are less computationally intensive architectures. You have like mobile nets for images. Next, we have the feature of multimodal learning, uh, advancements in transform models. Then we have edge computation, computing for multimodal data, real-time, multimodal AI, supervised learning. And these ones are like, because the multimodal learning has gone through ages. We have started whereby it is separate, is dealing with separate multimodals, then basic combination. Then now we have where we can merge more than 3 or 4 multimodals. So this is the future of multimodal learning. With the first one, the transformer-based models. We already talked about the transformers where we're using the neural network. These ones improve multimodal fusion, enabling more sophisticated and accurate representations. Real time uh, will benefit from faster inference. Then shall go to the next slide. Then we have our code here, image feature extracting. Now, I will first talk about feature extraction, although you have already talked about it. This is how do we get raw data to vectors. What we're trying to do here is attain raw data. One, well, the process we have is you get a raw data, then identify the important patterns. If you look through the code, that's basically what we're talking about. We have we identify the important patterns in this case, then convert the patterns into numbers. Then you combine them into the feature vectors that we are having. When you look through the code, the importing, then loading pre-trained data is getting our raw data. Then we have pre-processing, resize, crop, and normalize. So here we're converting the patterns to numbers that maybe a computer can understand. Okay, the next slide. Then we have the EGG. I think it's a EEG, electrograph. Now in this case, yeah, that's it. Thank you. This feature of extracting from signals, as we know that this EEG deals with brain signals, how the brain can, your brain reacts or responds to different, uh, let me say, environments, actions, regardless of how you as a person express yourself through facial expressions, through body languages. So the brain itself independently has things which someone can alter. So the EEG gives us a full definition of how someone is thinking or someone's response to this, someone's feelings. Basically, in this case, we're dealing with feelings. We have what we call the action potential that deal with the information attained from the brain. Now, in this case, we have what we call the time frequency analysis. Uh, Techniques like short-time frontier transformer or wavelet transformation I used to decompose EEG signals to time frequency. Then we have also the feature extraction method. These are common features that include power spectral density, the band power in various frequencies. We have the alpha, beta, theta, and etc. as the gamma. These ones give us the range of how, depending on the impulse, we call it impulse, amplitude of someone's feelings. Whether you're awake or asleep, we get the frequencies from these ones, alpha, beta, and theta, gamma, to maybe identify how someone's feelings are. The alpha could be the lowest, then going up to gamma. When someone's asleep, basically we are dealing with the alpha signals. Then we have fusion of EEG with other modalities like facial expression analysis, using the computer vision techniques, taking photos, analyzing someone's facial expressions using videos. Now, the computer is very important in that, or the machine, and helps us identify. Let me say, give an example: when a teacher trying to know the mood of the student whenever they're entering the lectures or the classes, by using facial expressions, so setting a camera at the doorway, analyzing the facial expressions, whether they're happy for the lecture, whether they are sad that day. So that helps a lot. Then we have also the audio analysis, analyzing the speech tone, the pitch, and other features. Now, some these occasions happen whereby you determine someone's emotion using uh, the voices, their tones that come out, the pitches, whether they're frustrated, angry, happy, or maybe sad, using the tones. And I think this marks the end of our presentation. We've been uh, discussing about multimodal planning, and I hope this has been helpful.